Triplanar mapping, the most well-known and established technique in the world of shaders. The hello world of people first dipping their toe into the art of advanced shader development. A way to map textures so convenient and versatile that literally every 3D game uses, with no exceptions. Then, why nobody implements it correctly? It's impossible that nobody ever noticed its problems and spent some time fixing them, isn't it? And yet, you might have noticed, everyone teaches the technique in the exact same way. How's that possible? A question that will stay unanswered, I'm afraid, but likely this issue will cease to exist with this video. What we are about to do is to go through the mainstream implementation of the triplanar mapping technique, analyze it, and finally fixing it. The triplanar is ubiquitous because the idea at its core is extremely simple, light and fast to implement, with a good visual outcome. We replace the mesh UVs with its vertex warp position data, after properly scaling it. But since the position is a 3-dimensional data, while the UVs have only 2 dimensions, we find ourselves having to make a choice of which of the 3 position channels to leave behind. Depending on our choice, we will obtain 3 different results, all falling into the macro category of the planar projections. Why planar? Well, because by mapping a texture this way is like having it on a plane that traverses the scene, spreading its pixels on the surfaces it encounters. So now I suppose that you can guess why the technique we're talking about is called triplanar. Because we map the same texture with all the 3 planes at the same time. Which implies the necessity of finding a way to calculate which plane should be shown on which part of the surface. As we can see, the more a surface is oriented towards a plane face, the more it makes sense to choose that to display, otherwise we will get just an extremely distorted mush. We can operate this choice by starting from the surface normals. If we isolate their components and remove the sign, we obtain a map of how much the surface is oriented towards that plane at any point. We calculate the max value of these 3, and for each of them we subtract from it one of the weights. This will generate an inverse mask for each channel, which we now can remap to the desired contrast. As last step, we normalize these weights by dividing each one of them by their sum. Now we can sample our texture 3 times, 1 for each plane, and multiply each result by its respective weight, and add everything up to combine it. And here's where everyone stops. You can see your texture correctly, word map, let's jump on the next thing. If it wasn't for the fact that the result seems correct, it is not. Let's give it a closer look. We correctly mapped the 3 planes on the right spots of our geometries, and we can now see the texture staying put in the world when we move the objects around. But at this stage we can already see a problem if we change texture. The lateral mappings are upside down, and one of their sides is also mirrored horizontally. The same thing happens on the bottom part of the projection along Z. This could be considered not a problem, since not necessarily all the textures look visibly wrong if transformed like this, but if you want to make a versatile shader, this thing must be solved. To do that, we can visualize the UVs one by one and fix them based on what we see. For a UV to be correct, we must see its colors arranged like this: black in the upper left corner, yellow on the bottom right, red gradient increasing horizontally, and green one increasing downwards. So, let's start by fixing the other side of this projection. The correction consists in multiplying the individual UV channels by either 1 or -1, depending on the cases. And to be sure to not break the other side, we can use the related projection normal channel sign. In this case, we just want to flip the V channel on the bottom part. So we create an append node that multiplies on the UVs, and we put a 1 in the first pin to leave the U unchanged on both sides, and we plug in the B channel sign for the V. This will multiply by 1 the upper hemisphere V channel, leaving it unchanged, and by -1 the lower hemisphere, inverting it. And now you can see that the colors match our reference. And we keep going like this until all sides are good. And now that everything seems to work properly, let's add the normal map. Let's have a look. Yup, it's completely broken. This problem is much more difficult to notice, but if we use this texture the engine kindly provides us, we can visualize it better. The fact it contains the normals of an hemisphere allows us to create a nice setup to check if our triplanar mapped vectors are correct. We can take a plane and overlap it with a sphere. Notice that if the normal map is being applied correctly, the colors generated by the texture hemisphere will match exactly the colors of the real sphere, which is not happening at the moment. If I make the base color a flat mid-gray, you can also see the plane catching the light from the wrong direction in the final pass as I rotate it. To understand how to fix these normals, we must first figure out why they're broken in the first place. By default, in a real engine, the normal maps are considered to be expressed in tangent space, which, for every individual mesh, it's computed from its first UV channel. So basically, it's like if every point on the surface considers as z-axis its vertex normal, and as x-axis the direction along the u of the UVs increases, and as y-axis the direction along the v of the UVs increases. And since we are not using the UV0 to map our normal map, the outcome is wrong, as the vectors contained in the texture don't match the tangent space anymore. And this is valid in all the cases where you don't use the UV0 for the normal map. Keep it in mind. Now, since we're using workspace data to map our texture, let's disable the tangent space option, which internally consists in this vector transform node hidden inside the normal pin. Disabling this option will make the output look even worse, but it's just a temporary thing. What's happening now is that the vectors contained in the normal map are being literally interpreted by the shader. Oh, you give me blue, so I guess this point on the surface is actually looking straight up along the z-axis, and so on. So what we need to do now is to create our own vector transform that will correctly interpret the texture vectors and properly translate them to workspace ones. We have to make one transformation for each projection. Let's start from the one along z, which is, by pure chance, the closest one to look correct. We know for sure, like in the usual tangent space, that our space z-axis will be the surface normal. Now we need to derive the other two axes. For the y, we can do a cross product between the surface normal and the world x-axis. Then, for the x-axis of our base, we can make another cross product between this newfound vector and the surface normal once again. One of three down. For the projection along y, we can copy the same base we just made, but we must invert the sign of the first cross product based on the sign of the projection. And lastly, for the x-axis, we can copy once again what we just did and swap the word x with the word y, and use the inverse of the projection sign. And now we can double check that everything is working properly with our plane sphere setup. By the way, I know that I made it look very easy and straightforward, but it is not. This is a sample of me trying to figure out the vectors to make these bases. It went like this for a couple of days. Anyways, you finally possess all the knowledge to implement a triplanar mapping worth of this name in your project. And I'll tell you more. You can avoid the hassle of making it all together and just download it for free by following the link in the description. Everything will be packed in a nice and tidy material function, ready to be used. Well, triplanar mapping can be considered as a relatively expensive technique, especially on memory side, as it forces you to triplicate every texture sample. This problem can actually be avoided if we are ready to compromise and give up the smooth transition between the different projections. The logic behind this mod is very simple. If we move the merging stage of the different projections to the UVs, we can map our texture along all three in just one go. The only thing we must change is the gradient we use for the blending, as it must now be a binary mask. This of course is not that simple with the normal map, as it requires one more step. In fact, we can now use the same pre-blended UVs, but then which matrix transformation do we use? All three at once, of course. By following the same logic of the pre-blending of the UVs, we must move the blending on an earlier point. In this case, we can observe how the nodes that we use to calculate the bases only differ in which is the input vector in the first cross product, so we can pre-blend this to then be able to run only one matrix transformation. Almost done. The only thing left now is to address the nemesis of UV's discontinuities. I've explained this problem more in depth in this other video, but for a quick summary, since along the seams the UV derivatives have very high values, the shader gets tricked into thinking the surface is very far away from the camera and samples one of the lowest resolution MIPs of the texture. To solve this problem, we must pass those derivatives manually to the samplers and calculate them using continuous data somehow. In this case, luckily, it's pretty straightforward. We simply calculate the derivatives of all three projections and then blend them as we do with the UVs. Since the masks are binary, the derivatives that will end up in every single pixel will be coming from just one of the three sources. And here it is, a lighter version of the classic triplanar mapping ready to use. Of course, this is included in the free download too. Now that we have a solid base, we can start behaving like if it was 2024 and this was an old technique that finally deserves a good modernization. The starting point for that is what we just built, a perfectly functional implementation of the triplanar mapping. Now, for how I see it, we have two possible routes to follow, defined by the two most common applications of the technique. Do we improve and specialize it for the usage on landscape and more in general for terrain building? Or do we take the path of modular assets that can be assembled to populate our environments? In this video we'll follow the first path, but don't despair if you're interested more in the other one, as there will be a follow-up video about that. So be sure to subscribe to the channel, join my Discord and maybe become also a Patreon like these amazing guys to not miss it. The issue I see at the moment when we use triplanar mapping on the landscape is that we're barely leveraging the lateral projections. If we pass through as color the projections weights, we can clearly see it. Even if this landscape has quite a lot of variety in terms of slopes, it's mostly only using the horizontal mapping. Consequently, we also have many areas where the textures we're mapping are very stretched out. What if we did something like this? If we reduce the inclination of the lateral projections, making them more horizontal, we improve their coverage and reduce the texture stretching at the same time. Let's see how we can do it. As first thing, we must identify the new lateral projections directions. We can define them starting from an angle mapped in 0-1 range that will tell us how much this new axis, that by default coincide with the word x and y ones, will align with the z axis. To create one of the vectors we need from this angle, we can use some basic trigonometry and calculate its cosine for its horizontal component, which goes in x, and its sine for the vertical one, which goes in z. This is the projection direction along the positive x. Now we can create a second vector by negating the cosine to have the one along negative x. We had to create the two mirrored directions individually because now, when inclined, they won't have the same direction anymore. To create the vectors along y, we just need to swap the positions of the first two components of the vectors we just created. To spare some space, and since with nodes we can't do a simple swizzle operation, I'll just use a custom node to do it. Here I'm just telling the node to take the input vector v and return a new one that has the v components in this other order. Now we have to merge these couples of vectors together by using the relative vertex normal component signs as masks. And we can dot product this projection axis against the vertex normals. All of this to replace the simple absolute node we were allowed to use before, because of the axis being perfectly horizontal. But now this section doesn't require any more work. The next adjustment needed is on the UVs. We now improve the coverage, but to reduce the texture distortion too, we must incline the UVs accordingly to the projection directions. While before we could just remove one component from the warp position, this time we have to operate a full transformation. The logic to follow is similar to the one we used for the normal maps. We first need to find the other two vectors orthogonal to the projection axis that will tell us in which directions the UV gradients will move. And then, to actually obtain our inclined UVs, we use them to dot product the position data. And we're done. Everything works properly. Or that's what I thought. Luckily, I have this habit of compulsively checking every single node I lay down before taking for good the material and start working at each video. At some point I just swapped the previous sphere for the cube and what the hell is going on? These kinds of artifacts are usually caused by some issues on the normals. More specifically, they happen when the normal is a vector of length 0. It must be something off in the transformation matrices. There you go, there are some completely broken sides here. We can see it even better by using the debug function to print out the faces values. These symbols are not ones, they represent a broken value. And by looking at what comes before the transformation, we can guess that probably the error is generated here, when this vector is normalized. Before carrying on, if you're wondering why we should spend all these energies with an issue that, it just happens on the cube, let me explain. It's not just about the cube, it's about every surface that has normals precisely aligned with the horizontal world axis. And we must care about this because on some hardwares, among which the PS4, to give you an example, a shader that outputs a broken value like this can cause random crashes of the GPU without any clue of what may have happened. And good luck in that case going and debugging an entire AAA project without knowing what you're looking for. Sadly, I talk from personal experience. Going back to us, we found the root of the problem. In the case the surface normal has the same direction of the projection vector, the cross product returns a vector of length 0, and a 0 length vector can't be normalized, since to do that its components must be divided by its length, and dividing by 0 is illegal. So the solution in this case might be checking the length of this vector beforehand, and if 0, overwriting it with the y-axis in this case. For the other two transformations we have to do the same, but this time the backup node is the x-axis. The bases we generate in these exceptions might not make mathematical sense, but it doesn't matter, because the error always occurs in an area that will be covered by one of the other projections. Now it's time to propagate the fix to the single fetch version of the triplanar. We must add both the checks together in the same spot. Since for the projections along y and z we use the same backup vector, we have just two cases to combine, which can be masked by the weights of the projection along x. Cool, we avoided potential catastrophes. Remember to propagate this fix to the previous version of the triplanar mapping. Let's now take a moment for ourselves to enjoy the fruits of our labor. As we initially said, we now have a much better coverage for the lateral projections, and the textures displayed show way less deformation. Since we're here, let's impose that the angle can't be set to 1. Who would actually try to set the lateral projections to be all in the same direction of the Z1, you say? If you're asking this question, it's a sign that you haven't worked enough in the industry yet. Anyways, you can download this version of the Triplanar mapping too by following the link in the description. And we could close it here, go to bed and get a nice sleep, but it's not what we're going to do. We can still get more from this texture mapping. We can go beyond what we just did and improve even more the plane's coverage and reduce furtherly the texture distortion. If we started with a triplanar mapping, and we could actually call the version we just made pentaplanar mapping, as the mirrored planes are not actually the same anymore. Get ready to make an n-planar mapping. It consists in a natural further logic step we can do starting from what we just built, which is to take all the 4 lateral projections and calculate them a second time while rotating the projection directions by 45 degrees around the z-axis. Will it be as easy to implement as it is to say it? Let's see. We begin our work from the section in which we calculate our projection axis this time too. The first thing to do now is to combine in just one pass all 4 the projections directions we had until now. Since this time it's not about combining projections along x and y anymore, but the 4 projections along x and y and the 4 projections rotated by 45 degrees. To merge the data we already had before into one, first thing to do is to rotate by 45 degrees the masks we used to merge together the pairs in opposite directions. I've saved these pi related values in named reroute nodes as we'll use them few times from now on. We need to rotate these masks because we want the seams to be in the same place as where they are in the single fetch triplanar version, to give you a reference. Now we need one more mask for the last interpolation though. A mask that is white for the planes oriented along x and black for the ones along y. To create it, we can add our rotated masks, subtract 1 and remove the sign from the result. Let's save this result in our named reroute node. Now let's take all this block and let's duplicate it. We must obtain the same result but with everything rotated by 45 degrees. Let's rearrange the order in which we append the components so that there's a moment where we have the 2D RG vector without the Z appended yet. This is our chance of rotating this horizontal component by 45 degrees. This means that our simple whistle is not good anymore and we have to replace it with a further rotation by 90 degrees for the second set of vectors. Let's execute the first pass of interpolations, this time without rotating the masks by 45 degrees. And the final one we keep it exactly as it is. Let's also save in 2 more named reroute nodes the cross masks, as we'll need them later. If we visualize the weights now, we see that the red channel highlights the areas along the word XY axis, while the green one is rotated by 45 degrees from them, while the Z weight becomes an octagon. Cool. This time no work is needed on the UVs. Last thing remaining is to update the bases for the matrix multiplications. For the first base we can combine together what we were doing previously in the first 2 transformations by using the first cross mask. We can keep the broken vectors in check by using either one node or the other, as now the error can only occur on the faces oriented along the z-axis. For the second transformation we can simply recycle what we just did now, change the cross mask and rotate the result by 45 degrees. And well, looks like it's working to me. Amazing. I admit that when I first thought about this I was skeptic about the idea actually working out. The very last thing we need to do is to update the matrix transformation in the single fetch version 2. And we're done! As we can see, the final result is definitely worth the extra work. By making a side-to-side comparison we can clearly see how the textures adapt in a much more natural way to the landscape. And we also obtain a little texture repetition breaking for free out of this, especially with the last version. Of course you can find this version too in the link in the description. And don't forget that there will be a follow-up video in which we'll specialize the triplanar mapping to work on props. So don't forget to subscribe and click on the bell to be sure to not miss it. See you next time.